Hi, I'm Joe CAULKINS, a master's student at Carnegie Mellon University studying computational material science. This summer, I investigated the relationship between cavitation strength and grain boundary misorientation angle using molecular dynamics as the primary workhorse. This study was sponsored by Texas A&M's online O-REU program, and my mentors this summer were Dr. Justin Wilkerson and Carl Favre. First, what exactly am I talking about here? Grain boundary misorientation is the degree of transformation required to change one crystal's set of axes into the other. Here, you can see the set of grain boundaries that I used this summer in order of increasing grain boundary misorientation angle. Molecular dynamics, or MD, is the tool that lets us see on an atomistic level of detail in these simulations. The way that MD works is by tracking properties of every atom, like XYZ coordinates, velocity, temperature vibrations, and bonds between atoms at each time step. The simulation progresses through these very small time steps using bonding physics to calculate how atoms will shift around. This gives us insight at a nanoscale that we look to extrapolate upwards to understand phenomena at larger length scales like spall behavior. Spall strength is critical in materials used in armor and other high strain rate applications. Understanding its dependence on grain boundary properties, like misorientation, is important for designing materials with tailored shock responses. Spall behavior is dominated by cavitation, the nucleation, growth, and coalescence of voids in a material. I studied cavitation strength, which strongly correlates to spall strength. On the left is a diagram of a flyer plate spall simulation done by Chen et al. This image in the middle shows another representation of a flyer plate experiment at the macro scale while showing the grains. Finally, the figure on the right zooms into one of these grains looking at it in the mesoscale to represent the same event with a smaller simulation. To put this difference into perspective, the simulations done by Chen et al. Used 15 to 20 million atoms. My simulations, modeled off the image on the right, are run on 20 to 25,000 atoms, 3 orders of magnitude smaller and faster. The goal of this study is to find a faster way to test cavitation strength of materials to aid high throughput design. I studied void nucleation behavior in a mesoscale simulation, like that shown on the right, to find the cavitation strength. I ran all simulations with Sandia's LAMMPS program for molecular dynamics and visualized them in O-REU. Like Chen et al., grain boundaries are all BCC tantalum, using the TA2 EAM potential file by Ravelot et al. To get a realistic grain boundary, I first must do a couple of things. I let this grain boundary on the left relax at room temperature, resulting in the one on the right. This removes unrealistic gaps between atoms, letting each atom resolve to their lowest energy position. Additionally, all materials have defects, so to simulate this, I use a pre-compression phase. The grains are compressed to about 40 gigapascals to nucleate defects, which matches the compressive stress from Chen et al.'s compressive phase. The GIF on the right has each atom colored by their centrosymmetry parameter. This is a measure of how far an atom's neighbors are from a perfect lattice, or in other words, a visualization of defects. At the end of the compression phase, you can see a significant number of defects surrounding the grain boundary. The grain in the middle is the same relaxed state shown on a previous slide, with clear defects in the middle and the top and bottom. These are grain boundaries, with those on the top and bottom because the simulation is periodic, so the grains are repeated infinitely in all directions to remove edge effects. The grain on the right is after compressing to 40 gigapascals and then pulling in tension back to the initial position. In addition to the grain boundaries, there is now a dislocation running diagonally in the top left, as well as smaller defects throughout. This shows the comparison between running the simulation with and without pre-compression. The tensile portion is the bulk of the simulation. The grain is pulled uniaxially until failure, and I measure the stress at which voids develop to find the cavitation strength. In addition to this boundary, I ran the simulation on 37 total grain boundaries, varying the misorientation on the same angles that Chen et al. Did. The graph on the left shows the average void nucleation stress from Chen et al. As the red closed dots, and my results as the blue open dots. On the right is a figure of their results showing 4 regimes of different failure behavior. These regimes fit best to a third-order polynomial, shown by the trend lines in this graph on the left. My results agree quite well here, seeing a similar trend that would display 4 regions. However, there is a vertical shift between our data. I investigated several possible effects influencing this vertical shift in cavitation strength. First, as mentioned previously, my simulations are run with 3 orders of magnitude fewer atoms. To find the effects of this, I varied the size of a single boundary up and down orders of magnitude. The rest of my simulations were run at the second point, with about 25,000 atoms, and I would need one more data point larger to reach the scale of the simulations from Chen et al. But there's already about a 2 gigapascal difference from size effects. The mean difference between our data was 2.28 gigapascals, so this could explain why there's a vertical shift in my data. This means, extrapolated to the same length scale, that our results would agree quite closely. In this graph, I varied the amount of precompression in the simulation from 0 to 50 gigapascals, linearly increasing compressive strain each time. With 0 gigapascal precompression, I'm trying to deform a perfect crystal, which is harder to do than when defects are present. The 0 to 20 gigapascal runs don't have enough stress to nucleate defects, so they all have similar cavitation strengths. The more interesting results come from the points around 35 gigapascals. The slightly lower point has 25% more compressive strain, but almost the same stress. That is because the compressive stress is partially resolved in the material by deformation. Thus, we can see that defects are generated at around 35 gigapascals. After that point, the cavitation stress does not decrease further when compression is increased to 50 gigapascals. There's just more damage to the system. As I use similar precompressive stresses to Chen et al. Of around 40 gigapascals, this likely does not describe the vertical shift. However, it does describe what is happening in the precompression phase. This graph shows the results of Chen et al. And my results after subtracting the mean difference of 2.28. This is just to compare the trends with misorientation apart from the vertical shift. My results agree with Chen et al. Quite well for lower angle boundaries around 0 to 100 degrees. However, they are off by more at higher degrees of misorientation. In the future, I hope to investigate why there is this difference. Also, note that despite a difference in the trend on the right side of the graph, there is no danger of extrapolating the line further, since due to symmetry, there aren't unique misorientation angles past 180 degrees. Starting this work, the goal was to find results similar to those from Chen et al., but using a simulation with 1,000th the size and computational time. My results agree quite well in trend, but with a vertical shift that is likely explained by size effects. If this method can accurately achieve a speedup of 3 orders of magnitude, you would be able to do something like what is shown on the left, in the same number of CPU hours as it takes to get one data point from Chen et al.'s simulation. You would be testing every percentage from 0 to 100 in composition in the tantalum-titanium phase diagram, as well as the temperatures 100, 200, 300 to 1000 Celsius. This method may make testing thousands of different alloy variations feasible to help designing materials in the future. Thank you for watching, and thanks again to Dr. Justin Wilkerson, Carl Favre, and Texas A&M's online O-REU program.